Okay, this is the notes for section 5.9 linear programming. If you haven't done so already, please make sure that you read this section. Really important reading section before going on. So once you've done that, then go ahead and start the notes again, and let's go through these examples. Okay. A linear programming problem is one in which you wish to find a solution to a system of inequalities that minimizes or maximizes a linear combination of variables. Okay, so in linear programming, what we're doing is we're trying to minimize or maximize something. Maybe it's minimize costs or maximize profit. Those are the two main areas that we'll be looking at. Okay, we want, if that's the case, if we want to minimize something or maximize something, we can use the linear programming theorem, and it says the following: the feasible region of every linear programming problem is a convex polygon in which the maximum and minimum quantity is determined at one of the vertices of this feasible region. Okay, so if we have a convex, it actually doesn't have to be a polygon, but a convex region. If we have a convex region, okay, it will always be maximized or minimized at one of the vertex points. Okay, so if you remember in 5.8 when we were looking at those regions and we were looking at those vertex points, the reason why we found those vertex points is because of the linear programming theorem. Okay, when we look at linear programming problems, here's the steps that we're going to follow to solve those problems. Then I'm going to go through an example where we walk through those steps. So first thing we want to do is identify the variables and write a system of constraints. Your variables will always be whatever you're trying to solve for. Okay. Step 2, it will be to graph that system and determine what the intersection of the lines defining the feasible region are. Step 3 would be to find the vertices of the feasible region. Okay, and to do that, basically we're solving a system of equations, kind of like we've been doing throughout this unit. Step 4, you're going to write a formula or an expression to maximize or minimize profit or costs. Step 5, you're going to apply that linear programming theorem to determine which vertices maximize or minimize your equation from the previous step. And then finally, step 6, you need to interpret the results and state your findings. Okay, so those are the steps that we're going to be following as we go through linear programming problems. Okay, let's walk through these steps for linear programming using example 1 here. It says, Lisa makes necklaces and bracelets in her spare time and sells all that she makes. Each week she has 10,000 grams of metal and 20 hours to work, which is 1,200 minutes. It takes 500 grams of metal for a necklace and 50 grams for a bracelet. Each necklace takes 30 minutes to make, and each bracelet takes 15 minutes to make. Okay, that's all the information we need to know for this problem. It says let n equal the number of necklaces and b equal the number of bracelets. So that's kind of the first thing we need to do, is assign our variables, and we're assigning them to the things that we're trying to find. Okay, Lisa makes each week. Find the vertices of the regions, the n, b pair. So n is going to be my x value, b is going to be my y value. Lisa can make each week. Draw a graph of the feasible region. Okay. Well, before we can draw that graph of that feasible region, what we need to do is we need to come up with a system of inequalities that we're going to graph to get that feasible region. Okay. So that's our first step that we're going to do here. Okay, let's begin then by looking at what are constraints. What keeps us from just creating any number that we want in terms of necklaces and bracelets? What's going to kind of keep us in check, basically? Well, there's two main areas that we have to worry about according to the information that we're given, and that is we only have a limited amount of metal, only 10,000 grams, and we only have a limited amount of time that we can use to make these, and that's 20 hours. Okay, so those are constraints that we have placed on us in terms of us making a profit here or limiting our costs. So what I'm going to do is I'm going to just make a chart kind of looking at each of those different situations. So if I look at metal used, okay, I know that I have a total of 10,000 grams of metal. I know necklaces use 500 grams and bracelets use 50 grams. So I can use that to help me come up with my constraint. Okay. The same with time used. I know necklaces use 30 minutes. I know bracelets use 15 minutes, and I only have a total of 1,200 minutes that I can use. Okay. So what I want to do now is I want to translate each of these into inequalities. Since each of these totals, it has to be less than or equal to those amounts. So it's got to be less than or equal to 10,000 grams of metal. It's got to be less than or equal to 1,200 grams or 1,200 minutes. When I write my inequalities, those are the inequality signs that I'm going to use. Okay, so I can say 500n plus 50b has to be less than or equal to 10,000, and 30n plus 15b has to be less than or equal to 1,200. Okay, setting up a chart like this to help you come up with your system of constraints can be extremely helpful. Now you'll notice underneath that I have two other constraints, and that is I can't produce negative values for the necklaces or the bracelets. I can't make -6 bracelets or anything like that. So I want to include that and know that my system has to reside in that first quadrant of my graph. Okay, step 2 is to graph the feasible region. So what you want to do is set up your graph so that you can do that. Okay, and you might want to play around a little bit with what your x and y intercepts are going to be, or in this case your n and b intercepts before you do that. But you want to set up your graph something like I have here, and then we're going to graph. Notice how I've already put it in the first quadrant, so I've really kind of already taken care of these last two inequalities. So it's really these other two inequalities that I need to take care of in order for me to graph this system. Okay, to graph that line, then I'm going to look at the easiest way to do it is to look at my x and y intercepts, or my n and b intercepts. And when n is 0, b would have to be 200, and when b is 0, n would have to be 20. So my two ordered pairs would be 0, 200, and 20, 0. So I'm going to plot and I'm going to graph that line using those x and y intercepts. Okay. Then I'm going to do the same thing with this equation right here. 30n plus 15b is less than or equal to 1,200. So I'm going to get my intercepts and then graph that. So my intercepts would be the 0, 80 and 40, 0 then. Okay. So if I plot those two intercepts and graph that line, I now have the constraints in there and graph. Now I just need to shade in my feasible region. Well, the feasible region has to be under both of these lines because they're less than or equal to, and then obviously it's in the first quadrant. So let's shade that region at this time. So this gray area then would represent the shaded region, or the feasible region shaded. Okay. Okay, the next thing we have to do is find the vertices of the feasible region. Well, to do that, three of the vertices are very easily found. One is 0, 0, obviously the intersection of n equals 0 and b equals 0. The second one, 0, 80. Okay, 0, 80 would be the y-intercept of 30n plus 15b equals 1,200. And the third one, 20, 0, is the x-intercept of this. And those x and y intercepts we already found in terms of graphing the equation, so those were vertices that were easy to find. The last vertice that we need to find is the intersection of these two lines, which means that we have to solve the system of these two as equations. And you can use any method you want to do that. If you would prefer to use graphing, you can do that, matrices, whatever works best for you in terms of solving that. But we're going to need to solve that system. Okay? Once you do that, you can get this point right here. So what I did is I used matrices to solve that system. Like I said, you can use any method that you'd like. And here's my work for solving that using matrices. So I came up with the point 1550, so that would be the other vertice of my feasible region there. Okay, part A took us through the first 3 steps of linear programming problems, and part B will take us through the last 3. It says Lisa's weekly profit is $8 on each necklace and $5 on each bracelet. How many of each type of jewelry should Lisa make and sell each week to maximize her profit? Okay, so what we want to do is we want to start by writing a profit equation based on that information. Okay, so based on that information, our profit equation would be 8 times the number of necklaces that we make plus 5 times the number of bracelets would equal that total profit. So that's step 4, writing that profit or cost equation based on the information that's given. Okay? Now, we know from linear programming that our profit will be maximized at one of the vertices. So what we want to do is we're going to try each of the vertices in the profit equation to see which one gives us the most profit. So if I look at the profit at each of the vertices, plugging in each one of them, you can see what my profits would be. Okay, so I get no money at 0, 0, $400 at 0, 80, $160 at 20, 0, and 1550 we get $370. Okay, well, we know that these are possible places where we can maximize them, and obviously the place where it's being maximized is at the point 0, 80. So what that means for us is that she should produce no necklaces and 80 bracelets.